And good morning, everybody. I hope y'all had a wonderful weekend and that you had a nice Monday. You're able to ease your way back into the school week. As you all know, grades were posted yesterday. The end of the grading period was on Friday. I tried to include as much as I possibly could for everybody in their progress report. I did grading up through like Sunday night and Monday morning. And posted grades like right at the deadline. So I gave everyone as much time as I could to get stuff in. If you are not happy with your grade, you still got about a little over like 12 weeks of school left to make it better. Remember, anything you've submitted already, you are more than welcome to submit again, make corrections and resubmit to improve your grade. So if your grade wasn't accepted, or if you didn't self-assess a grade and I gave you a grade you didn't think you deserved, look at the feedback, look at the comments, make some corrections and resubmit. So please take advantage of that. Also on the same page as the free response questions, solutions and things, more particular talking with chapter 6, because I've had a lot more responses for the chapter 6 FRQs than the chapter 7 ones so far. I noticed a large amount of you guys making the same error based on the same work. And so I Google searched the questions to see if you guys were possibly getting these results from a source. I was able to find some of those responses with the incorrect work and methods that are beyond the scope of this course online, which is fine. You're not gonna lose credit for using a resource that you have available to yourself. I did that in classes as well. If I don't know what to do, I need to figure it out. I've definitely Googled how to do problems and Google searched specific problems to find out how to do them. That's okay. But you need to make sure you understand what's being done, that it makes sense, don't just copy it, and that it's correct. Now, I know it's hard to say whether or not it is correct. I mean, like, put that in your calculator to make sure you're getting the same result kind of thing. The reason I say this is because I have recently found out that the questions I use on the free response parts of the assessments are like copywritten questions from College Board. I'm allowed to use them. I have the right to use them as I'm an approved AP teacher, but they're not supposed to be out there in the world, so to say, as far as like on the internet with solutions. Now, obviously, they cannot stop people from posting them into those like websites that provide worked solutions, and people post solutions and things like that. However, there are teachers and professors who work for College Board and for AP who check to see if these questions have been posted anywhere. And to combat these things happening, they post incorrect solutions. And they upvote those solutions so that they show up, and then people copy them and they get things incorrect. So be aware of that. This is something that they are doing to try and combat these questions being posted online, because there's more of them being posted this year due to online learning. And so they're posting incorrect solutions. So if you found solutions doing this, which again, I do not fault you for doing, I've done it myself. You need to make sure and check it as best as you can for accuracy, and that you can make sense of it. Because there's wrong solutions out there on purpose. These teachers are doing it on purpose to penalize students who are using these resources. So if you were told that you did something incorrectly, but you're like, well, I found that on, someone found the solution and we all thought it was correct. The method may have been okay, the formula may have been set up correctly, but the solution was ultimately incorrect because whatever reason, I don't know. It could have just been a calculator error, which is what I defaulted to on most of the comments. It's like, hey, you probably just put in a calculator wrong. That's fine. People make calculator errors, so your formula was correct. But when I see the same exact formula with the same positioning of things and the same incorrect result, the wheels start turning, and I try to figure out why that's happening, and this is what I came up with. Whether it's true or not, this is just my observation. No one has told me that this is what they've done. I don't care, to be honest. If this is what you're doing, that's fine. You're using the resources you have available to yourself to learn and understand something. Cool, that's fine. I am not going to fault you for it. But you are responsible to make sure that you understand it and that you can perform those calculations on your own. Check them. Okay, so any questions about that? I wanted to make sure and be transparent with you guys and that you know that I understand that this goes on and that there's some things out there that are incorrect. All right. So just be careful. Very cool. And honestly, I'd rather you just ask me if you need help or clarification. I'd be more than happy to help you work through problems or do other problems that are like use different numbers so you get a better idea of what's going on. That's fine. Okay. So thank you for listening. Bit of a rant. I apologize, but something that needed to be said. With that, we are going to be doing section 8.2 today. I have abandoned my idea of trying to do 8.2 and 8.3 in one day. It is just not going to be possible. 8.2 and 8.3 just have too much going on, and they need their own day and activity associated with them so that we can make sense of it. So that's what we're going to start with today is section 8.2. I do recommend that you have something to take notes on already. You obviously do not need to copy everything. You don't try to copy everything from the slides, but there are some formulas and rules that you do need. And you're going to want to have available in your notes to be more familiar with them. All right, so we're going to share my screen. Alrighty. So here we are, chapter 8, estimating with confidence. We're dealing with section 8.2, estimating a population proportion. The entire section today will deal with proportions. Right, so we're going to be dealing with P and P hat and those types of formulas. All right. These are our objectives for today. These are the things we want to start becoming familiar with. How to state and check the random 10% in large counts conditions for constructing a confidence interval for population proportion. Notice 10% in large counts. Those are things that we already checked previously in chapter 7 for proportions. We need to be able to determine critical values for calculating a C% confidence interval for a population proportion using a table or technology. We want to be able to construct and interpret a confidence interval for a population proportion and determine the sample size required to obtain a C% confidence interval for a population proportion with a specified margin of error. We will see examples of all of this today. So first we have specific conditions that we must check before estimating P, right, or a parameter P population proportion. Before constructing a confidence interval for P, you should check some important conditions. And they're here. We need to check that it is random. The data came from a well-designed random sample or randomized experiment. Right? In other words, they tell you in the problem, so-and-so took an SRS of 50 individuals from the population, or an SRS of 70 people from a population of 1,200. Right? That tells us right away it's random. It's an SRS. If you see they sampled the first 50 people that walked into the school, that's not random. That's convenient. Right? That fails the random condition. Right? So we need to be checking for randomness. 10% condition when sampling without replacement. We need to check that n is less than or equal to 1 over 10 times n, where little n is the sample size, big N is the population size. And so again, we're checking our 10% condition. This is mostly important when we're sampling without replacement, hence the condition without replacement, meaning we're sampling by surveying people, right? We're not going to ask the same person twice for their opinion. We could sample with replacement, like have a sack full of different colored beads, and I'm going to pull a sample of 15 beads, see how many of them are red, put it back, take another sample, right? That could be sampling with replacement. That could happen as well, in which case we wouldn't necessarily need to check 10% condition. We need the large counts condition, right? Meaning the number of successes and the number of failures are at least 10. These things must be true in order for us to construct a confidence interval about a proportion. So we need a moment to write these things down. Please raise your hand. All right. So when we construct a confidence interval for P, right, we can use the general formula from section 8.1 to construct a confidence interval for an unknown population proportion P. Okay, so this is what we saw last week. We take our statistic, in this case P hat, plus or minus the critical value, right? How many standard deviations do I want to be close to the actual parameter? And multiply that by the standard deviation of the statistic, standard deviation of P hat. Right? The sample proportion P hat is the statistic we use to estimate P. When the independent condition is met, meaning that knowing one outcome has no effect on the next outcome, the standard deviation of the sampling distribution of P hat is, as we found previously, sigma P hat equals the square root of P times 1 minus P divided by N. Since we don't know the population parameter P, we replace it with the sample proportion P hat, and this gives us the standard error of the sample proportion. And that is the square root of P hat times 1 minus P hat divided by N. And we can use the notation S with a subscript P hat to represent this, or you can just say SE, like big letters SE equals. Right. When the standard deviation of a statistic is estimated from data, the results are called the standard error of the statistic. Right, so we don't call it the standard deviation, we'll call it the standard error. Right. You raise your hand if you need a moment to write anything down. So how can we find the critical value for our confidence interval, right? We're going to need that number. Again, we have our formula, statistic plus or minus critical value times standard deviation or standard error. If the large counts condition is met, which we should have already checked, we can use a normal curve. To find a level C confidence interval, we need to catch the central area C under the standard normal curve. Right, so we have our standard normal curve here. We're trying to catch the 95% confidence interval in the middle. That leaves 5% split between each tail evenly. Right, so to find a 95% confidence interval, we use a critical value of 2 based on the 68, 95, 99.7 rule. This is what we've been using. Using table A or a calculator, we can get a more accurate critical value. Right, we get a critical value Z asterisk, right, this little star, right, is actually 1.96 for a 95% confidence interval. So we're at negative 1.96, positive 1.96. This is a more accurate value than using 2. Again, the 68, 95, 99.7 rule is like a general thing, like, hey, write about these, intervals is where these things are. We can be more exact. Is there anything I can clarify here? And we use this z asterisk to represent the critical value. It's very similar to a z-score, but it is not the same as a z-score. It represents something slightly different. So we're going to do an example here of finding a critical value. All right, we're going to use table A to find the critical value z asterisk for an 80% confidence interval. We're going to assume that the large counts condition is met, meaning we can use the normal curve. Since we want to capture the central 80% of the standard normal distribution, we leave out 20% or 10% on each tail. Right, so the probability in the middle is our 0.8, right, 80% of the curve. That leaves 0.1 to the right, 0.1 to the left. We search table A to find the point z asterisk with an area 0.1 to its left. So here's our little section of table A. The values of 0.1003 and 0.0985 are the two values closest to 0.1. 0.1003 is closer to 0.1 than 0.0985, so we're going to use the 0.1003 value. Right. So the closest entry is z equals negative 1.28. We get that from the negative 1.2 plus 0.08, negative 1.28. The critical value z asterisk, or z star, for an 80% confidence interval is 1.28. Notice we just take the value. We're not including the negative here. We're just saying, okay, well, the critical value is a distance. Distance is always positive. My critical value is I'm 1.28 standard errors or standard deviations away from my statistic. So we don't need to take the fact that it was negative from table A here. See, we need a moment to write anything down. So the method we're using is a one sample z interval for a population proportion. Right? And this allows us to determine the interval, right? And it's a one sample because it's based on a single sampling from our population. Z interval because we're using the z value from table A. Or population proportion. This is allowing us to calculate our interval. Once we find the critical value z asterisk, our confidence interval for the population proportion P is essentially what we've seen before, statistic plus or minus critical value times standard deviation of a statistic, except to replace everything with things having to do with our sample. So we have the statistic of P hat plus or minus critical value Z star Z asterisk times the standard error, square root of P hat times 1 minus P hat over N. Right. And this is the rule that we're using, right? The one sample Z interval for population proportion. Right. When the conditions are met, right, meaning random 10% large counts, a C% confidence interval for the unknown proportion P is P hat plus or minus Z star times the square root of P hat times 1 minus P hat divided by N, where Z star is the critical value for the standard normal curve with C% of its area between negative Z star and positive Z star, which is what we saw on the previous page. Is there anything I can clarify about where all these variables came from or why we're using them? Does anyone need a moment to write any of this down? So this you're definitely going to want. So we're going to consider an example here. So suppose that we took an SRS of beads from a container and got 107 red beads and 144 white beads. This container only has red or white beads. And we're assuming this is a large container. We want to calculate and interpret a 90% confidence interval for the proportion of red beads in the container. Right? I claim that there's 50% of the beads are red. We're going to use the interval we find to comment on this claim. Right? We can calculate the sample proportion, or p hat, based on this sampling of 107 divided by 251, and we get 0.426. Right, and the conditions, right, are randomness. This is an SRS, 10%. Right, 251 is less than 10% of all the beads in our large container. And large counts, 107 and 144 are both greater than or equal to 10, so those have all been met. All right, so we're going to use table A, right, and we need to find our Z asterisk. Right, for a 90% confidence level, Z asterisk is 1.645. Right, we get this because if we're at 90%, that leaves 10% to split between the two tails, which means each tail represents 5% or 0.05. These are the two values closest to 0.05. They're both the same distance from 0.05. So we split it. And we use negative 1.6 and 0.045, the value between 0.04 and 0.05. And that gives us negative 1.645. And for the Z star, we use that positive number, 1.645, because we're just concerned about distance. So we remove the negative for this. We then need to calculate the interval, right, which is p hat plus or minus Z star times the square root of p hat times 1 minus p hat divided by n. So we get 0.426 plus or minus 1.645 times our standard error, square root of 0.426 times 1 minus 0.426 divided by 251. And we get 0.426 plus or minus 0.051, and it gives us the interval of 0.375 to 0.477. So these are our probable, right, or plausible values for the actual parameter p. Right, we are 90% confident that the interval from 0.375 to 0.477 captures the true proportion of red beads in the container. Since this interval gives a range of plausible values for p, and since 0.5 is not contained in the interval, we have reason to doubt the claim. Notice in the verbiage here, we're not saying that the claim is wrong. We don't have the evidence to make that claim. We have the evidence to say that we have reasonable doubt. There's reason to believe it's incorrect, but we can't say that it is wrong, because in order to make that claim, we would have to sample the entire population of beads, right, which might not be worth our time, but we can say, hey, we have reason to believe this is not true. Right? So you have to be careful how you word things. Is there any questions about this example? Anything I can clarify? Does anyone need a moment to write anything down? Now, here's our 4-step process for confidence intervals for proportions, which we can also translate for means. This is to help us stay organized. The textbook shows up with this 4-step process a lot. in different contexts. This is for what we're doing here with confidence intervals, right? And they have this 4-step process because on the AP exam, the graders and such expect you to kind of go through this type of process. You don't want to leave any parts of these steps out. Right. So we want to state what parameter do you want to estimate and what confidence level, and at what confidence level. Essentially, what are you going to be doing? Tell them what's up. Plan, identify the appropriate inference method. In this case, we have the one sample Z interval method that we've just seen. We need to check the conditions for that method, meaning our random 10% and large counts. If the conditions are met, perform calculations. And conclude. Interpret your interval in the context of the problem. This is important. You could do state, plan, and do, show all the math and have all the things there. But if you don't make your conclusion, you're not going to get full credit. If you don't make that one like summary statement or sentence saying this is what this interval represents, this is what it means, you haven't fully answered the question. Okay, doing all the calculations is great. You understand the math, you can do that. That's part of it, but it is only part of it. You have to put it all together. Okay. See, we need a moment to write this down. So the next thing we're going to look at is how to choose a sample size. Right? There are scenarios where we want to make sure we sample enough so that we can have a certain amount of confidence and only a certain amount of error or possible error. And this is important because sometimes sampling costs money, right? If that's what your company does, they do surveys and polls and things like that. Oversampling, like creating too large of a sample, could spend money they don't necessarily have to spend. So it's good to know ahead of time, like, hey, how many people should we survey to get a result that within a certain margin of error and confidence, right, ahead of time. So in planning a study, we may want to choose a sample size that allows us to estimate a population proportion within a given margin of error. The margin of error, ME, in the confidence interval for P is, right, the thing that we're adding or subtracting to the statistic. Right? ME equals Z star times square root of P hat times 1 minus P hat divided by N. Z star is the standard normal critical value for the level of confidence that we want. Because the margin of error involves the sample proportion P hat, we have to guess the latter value when choosing N. There are 2 ways to do this. So again, since we're trying to choose the sample size before taking the sample, we don't have a sample proportion to use in our calculation for the margin of error. So we have to guess. We have 2 options on guessing P hat. Option 1 is to use a guess for P hat based on past experience or a pilot study. Right? Maybe there was a smaller sample done and there was some result that's usable, right? And we can try that, or we can make an educated guess based on what we already know. The other option is to use that P hat is equal to 0.5 as the guess. The margin of error will be largest when P hat equals 0.5. So that means if we use P hat equaling 0.5, we're guaranteed to be within that margin of error. Right? It's going to work for us. Right? It might give us a larger interval, right? But our margin of error will be where we want it. Right? So these are our 2 options. And so we can kind of boil this down to this here. Right? To determine the sample size N that will yield a level C confidence interval for a population proportion P with a maximum margin of error ME, solve the following inequality for N. Right? We have our margin of error from calculating our interval, right? Z star times the standard error, right, less than or equal to the margin of error, right, where p hat is a guessed value for the sample proportion. The margin of error will always be less than or equal to ME if you take the guess p hat to be 0.5. Right? So there's that. We'll see an example on how to do this next. Does anyone need a moment to write anything down? So here's our example here. Determining sample size. A company has received complaints about its customer service. The managers intend to hire a consultant to carry out a survey of customers before contacting the consultant. The company president wants some idea of the sample size that she will be required to pay for. One critical question is the degree of satisfaction with the company's customer service measured on a 5-point scale. The president wants to estimate the proportion P of customers who are satisfied, that is, who chose either satisfied or very satisfied, the two highest levels on the 5-point scale. She decides that she wants the estimate to be within 3%, 0.03, at a 95% confidence level. How large a sample is needed? So the problem is that we need to determine the sample size needed to estimate P within 0.03 with 95% confidence. The critical value for 95% confidence is Z star equaling 1.96. This is from previous results on this presentation, that 1.96 is the better estimate for our 95% confidence interval over 2. We have no idea about the true proportion P of satisfied customers, so we decide to use P hat equaling 0.5 as our guess. Because the company president wants a margin of error of no more than 0.03, we need to solve the equation that our margin of error is less than 0.03. So this is just like all the setup. This is everything we know before we've done any calculations. All right. So here's our equation. We have 1.96, that's Z star, times the standard error, less than or equal to 0.3. We need to multiply both sides by square root n and divide both sides by 0.03. And that gives us 1.96 divided by 0.03 times the square root of 0.5 times 1 minus 0.5 is less than or equal to the square root of n. Square both sides. We get 1.96 over 0.03 squared times 0.5 times 1 minus 0.5 is less than or equal to n. We use our calculator and we get 1067.111 is less than or equal to n, which means n is greater than or equal to 1067.111. We round up to 1068 respondents to ensure that the margin of error is no more than 3%. Right? It's an inequality. It says n can be any value equal to or larger 1067.111. So we can round up and still satisfy the inequality. We cannot round down. We can't round down to 1067 because that would be in violation of the inequality. Right. So any questions about this example or the calculations that were used? So that brings us to the end of this presentation. Now what we're going to do next is I have a couple more examples that we're going to work through to see how to apply these concepts again. And this is based on some of the feedback that I got from the free response question self-assessments, the reflection, that many of you guys would like to see some more examples. So I have some examples. And these are selected because they have multiple parts and require us to use all of the things that we saw today. All right, so we're going to switch over to examples, which are right here. All right, so here we go. Let me adjust some things. Extra space here. All right, so our first problem here that we're going to look at is actually based on a context that we saw last week in our practice problems on Wednesday. Tanya wants to estimate what proportion of our school's seniors plan to attend the prom. All right. She interviews an SRS of 50 of the 750 students, or seniors, in her school and finds that 36 plan to go to the prom. Okay. So part A is identify the population and parameter of interest. All right. Our population is the seniors at the school. All right. All right, and the parameter of interest is the proportion of seniors who plan to go to the prom. Right. So that is the answer for A. Right. Notice I'm not just saying seniors and proportion of seniors. Right. I'm writing complete sentences to answer the question. This is the kind of the expectation when you answer questions for the AP exam. Don't just put a one-word response. You should write it as a sentence. We need to check conditions for constructing a confidence interval for the parameter. Right, we have 3 conditions to check. Is it random? Right, is the 10% condition met? And the large counts condition. Right, is it random? Yes. Tanya took an SRS of students. That's random. 10% condition. Right, since 36, wait, not 36, 50. 50 out of 750 is less than or equal to 10%. 750. 10% condition is met. And finally, our large counts condition. Since 36 and 14 both. I don't want to say it that way. Greater than 10. The large counts condition is met. Right, so we checked our conditions, everything is good, right? So we can use our normal curve for helping determine our confidence interval for the parameter p. Right, and we can actually we can find the confidence interval because the conditions are met. So we need to construct the 90% confidence interval for p. We need to show our method. Right. So we have a few things to do here. So we're going to use the one sample z interval for population proportion as our method. Right. We want to find the 90% confidence interval. Right. We have p hat equals 0.72. And that's our 36 divided by 50. We know, let's see, if we're at a 90% confidence interval, right, and this leaves 10% for the tails of the standard normal curve. Which is 0.05 for each side. Right. So we need to find 0.05 on table A. Right. We did this. We saw this in the presentation earlier. Right. 0.05 right, results in a z-score of negative 1.645. All right, so we get a z star of 1.645. Right, and this is our critical value. Right. So then we can now calculate our interval. And we use our formula, right? Statistic plus or minus critical value times the square root of p hat 1 minus p hat over n. So we replace all this with the numbers that we have. We get 0.72 plus or minus 1.645 times the square root of 0.72 times 0.28 divided by 50. And we get 0.72 plus or minus 1.645 times 0.0635. And this gets us to our interval, which we get 0.616 as the lower bound and 0.824 as the upper bound. Oops. Okay. So we've constructed our confidence interval for P. We've shown our method. We now need to interpret the interval in context. Right. And we use the statement that we saw from last week for interpreting a confidence interval. Right. We are 90% confident. Yes, Jose, do you have a question?
Yeah, how do you find p hat?
P hat was from our sample. So we had our 36 out of 50 students who said they wanted to go to the prom. Right, so P hat is the sample proportion.
Okay, thank you.
You're welcome. Okay, so we're 90% confident that the interval from 0.616 to 0.824 captures the true proportion of seniors who plan to go to prom. Right. So when we interpret, we need to provide the context that this thing is talking about. It's not enough to say that we're 90% confident in the interval from 0.616 to 0.824 captures the true proportion. That's incomplete. It captures the true proportion of seniors who plan to go to prom. That's the context from our problem. Is there anything I can clarify or explain in better detail? All right. So moving on to our next example. All right, so a national opinion poll found that 44% of all American adults agree that parents should be given vouchers that are good for education at any public or private school of their choice. The result was based on a small sample. Right, they're giving us this information because we need to guess the value for p hat. Right, and so we're going to use this previous result as the value of p hat, and that's what it tells us to do in part A. All right, we need to determine how large an SRS is required to obtain a margin of error of 0.03, right, plus or minus 0.03, in a 99% confidence interval. Right, we answer this question using the previous poll's result as the guessed value for p hat. Right, so we have to start p hat is 0.44. Right. We have a margin of error of 0.03 that we're looking for, right? We have a 99% confidence interval. Right, this means we split 1% between each tail, right? And that means we get 0.005 to find on table A. Right, and this way we get our critical value, our Z star. Right, we need to find 0.005 on table A. Right, because Z star is the value that we're missing besides it, the sample size that we're going to solve for. So we look over here on table A, and we get these values here, 0.0051 and 0.0049. That's the two closest values to 0.005. We're going to just take the middle, right, because 0.005 is between those two. So we'll use negative 2.5, and then in between 0.07 and 0.08 is 0.075. So we'll use that as the last part of our decimal, and we'll use the Z-score of negative 2.575 to determine Z star. So we get a Z star equal to 2.575. Right, now we have all the pieces we need to set up our equation, or our inequality. All right, and so again, the equation or the inequality that we're using is Z star times P hat 1 minus P hat over N is less than or equal to the margin of error. So we replace everything with the values we have. We get 2.575 times the square root of 0.44.56 divided by N, we don't know N yet, is less than or equal to 0.03. Does everyone see where all these numbers came from? Does anyone need me to clarify where we got these values? All right. So now we have to do some fancy footwork here and rearrange this so we get N being greater than or equal to a value. So first thing we're going to do is break up the square root. Right, and this is based on, a square root rule. If I have the square root of A over B, that is equal to the square root of A divided by the square root of B. So I can break this up so that I can get N by itself, which I need to do. So we end up with 2.575 times the square root 0.44, 0.56 divided by square root of N is less than or equal to 0.03. Right. So then I multiply each side by the square root of N and divide each side by 0.03. This moves things around to where I get N on the right-hand side of the inequality and numbers on the other side. All right, so in this step, we take square root of N divided by 0.03. Do the same thing on this side, square root of n divided by 0.03. Right, the square root of n cancels on the left-hand side, 0.03 cancels on the right-hand side. Right, and we're left with 2.575 times the square root of 0.44, 0.56 divided by 0.03 is less than or equal to square root of n. We square each side, right? That gets rid of my square root sign. Right? These things cancel each other. Right? And we get n is greater than or equal to 1,815.32. Right? Which means we need an SRS of size 1,816. We'll round up, right? Because again, I have to round up. I don't have the option of rounding down to 1,815 because that would violate the inequality. Right, to obtain a margin of error of 0.03 in a 99% confidence interval. Right. And so again, we're taking the result and we're summarizing it in this statement at the end. That's part of our solution. It needs to be there. Is there any questions about the math that just happened? So then the last part here, answer the question in part A again, but this time use the conservative guess p hat equaling 0.5. By how much do the two sample sizes differ? I made an error. I have an extra question mark, but that's okay. All right, so to do this part, since we've done a lot of the calculation things and finding of values already, we're going to use a shortcut. And this is based on the work that we just did. Right? Based on what we just did, I can kind of directly calculate n, or solve the inequality for n, by using the already rearranged equation. Right? The original, right? Z star square root of p hat 1 minus p hat over n less than or equal to margin of error can be rewritten as n is greater than or equal to z star times the square root p hat 1 minus p hat divided by margin of error, all of that squared. Right, that's what was left when we rearranged our equation, right? So I can pop all this in and just replace p hat with 0.5 for my original. So we get that n is greater than or equal to 2.575, our z star, times the square root of 0.5, 0.5, our new p hat, divided by 0.03, margin of error, squared. We can put all of this directly in our calculator, and we get n is greater than or equal to 1,841.84. All right. So we would need sample size of 1,842. Respondents. Which is 26 more. Part A. Right? And that's it. What questions do you have? What can I clarify for you? Okay. So then that wraps up the lesson for today. As kind of our pattern has been, tomorrow we will do some practice problems as a class. We'll have an activity ready for us to get more practice using these concepts about estimating population proportions. And if you have any questions between now and then, please let me know. The practice problems for section 8.2 will be ready shortly. I haven't quite finished typing them up. And I will notify you guys when those are posted, along with I'll also post the problems that we just did so you can reference those. All right. So other than that, I will see you all tomorrow for more practice. Have a great rest of your day.